So I'm going to cover a couple different topics. I'm going to give a very high-level overview of the architecture and security concepts, and then I'm going to talk about some considerations around performance and deployment, and then a little bit about the open source project, like how you get the code, etc. So what is Alljoyn? It's your platform and bearer-independent networking. So for devices and applications is pretty key. Alljoyn is really built around the idea of applications talking to each other, not devices. And that will make a little bit more sense as I work my way through it. So why is it that peer-to-peer is hard? So part of it is this whole ad hoc networking thing. There's security. There's pairing of devices, which if anybody's done anything with Bluetooth, I'm sure you're familiar with that. And then there's discovering devices, but even once you've discovered a device, what are the services running on that device? What is it that you're actually interested in interacting with on that device? It's not necessarily the entire device. Anybody with a smartphone has like 80 things running at the same time, right? That's why we're all in this room. And then there are different platforms, and then radio, and then devices coming and going as well. So the goal of Alljoyn is to make peer-to-peer frictionless, and the way we do this is by enabling discovery. So how do you discover these devices and the applications? The ability to adapt to devices coming and going from the network, i.e. a truly ad hoc network. Managing the transport so the developer that's using the SDK doesn't have to worry about whether it's Bluetooth or Wi-Fi or whatever new transports, Wi-Fi Direct, come along. The ability to interoperate across different operating systems. So you could have an app that is written for Android that can then interact with a PC, for example, or a Mac or something like that. And we've written a bunch of apps like that. Unfortunately, I didn't get my act together, so I don't have any demos to show you guys, but I can certainly talk to it. And then the ability to exchange information and do so in a secure manner. That's another thing. When you're talking about ad hoc networks, how do you make sure that you are actually exchanging that you're exchanging information with who you think you're exchanging information with, and security as well if you need it. So what experiences do we expect this to develop, or enable, not develop, sorry. So things like social, like friends that are around you, proximal awareness, so for example, it could be used by stores or whatnot to deliver coupons when you're close to wherever those coupons are relevant. Media sharing, chat, multiplayer gaming is a big one that most people can relate to. And then, and I already talked to the coupons and the rewards. So that's kind of a high level to give you sort of a taste of what it is. I'm going to talk a little bit about the architecture and the security concepts. So Alljoyn was designed to be easily portable across OS platforms. So that doesn't mean that it's free, but it was architected in such a way that all of the platform-specific stuff was very isolated from the core functionality. The core functionality itself is not tied to the platform in any particular way. And it's basically a distributed software bus, and I have a picture to talk to some of these points, so I'll talk more about them there. The bus formation is ad hoc. So basically, as two devices come into proximity with each other, if there is a reason for them to establish a bus connection because there are services and applications that want to interact, the bus will be formed at that point. And then the protocol is link independent. So we actually did a ground-up implementation of the dbus wire protocol. So how many people here are familiar with dbus in any way, shape, or form? Okay. So, and then we added some extensions to enable the peer-to-peer piece of it. dbus, as those of you who have dealt with dbus, is really focused on the device. And we took that concept and expanded it cross-device, and that's where things like security and whatnot came in. We currently support Wi-Fi as well as Bluetooth, and we're working on Wi-Fi Direct support as well. So the distributed software bus. So you can see that the architecture is basically, there's a daemon that manages the device-to-device interaction. It's the thing that extends the bus across devices, and then applications interact directly with the daemon. And the daemon is the one that does all the message routing. So for example, you see, device 3 has an app Z and device 2 has an app Z, assuming those are peers that want to interact. It's really through the daemon that they do that. The other thing to sort of take away from this is that the relationship between the devices is totally independent of the actual applications that are running on there. So,
can we ask questions?
Yeah, sure. So long as I don't overrun my time.
You're saying the device runs 2, 3, is this running on kernel level or application level?
The daemon is a user space daemon. Does that answer your question? Yeah, it's not a kernel daemon. It's a daemon, so it's a user space process. And I have a picture of how it fits into Android later too. So, but the thing to note is, the bus exists across the 3 devices because each of these devices have applications that wants to interact with the others. So the peers in this model are really the applications, not the devices themselves. And so I talked about pairing earlier. Bluetooth has this device pairing model. And the problem with that in the app world that we live in is I don't necessarily want to give you access to anything except, say, my business card. But if we have to pair our devices in order to exchange our business card, you can now download my entire address book, right? And so Alljoyn kind of steps back from that and says, no, I don't want to pair devices. And I'll talk a little bit about this as well. I just want to be able to exchange whatever this peer-to-peer app is. And so the model is really built around the application and its application level security. And I think I covered everything else on here. So Alljoyn encompasses all of this functionality. So, you've got peer sessions, you've got, message expiration, so on and so forth. And a lot of the stuff in the center you will recognize is basically being dbus. And Alljoyn, the implementation is 100%, we believe, we haven't actually tested this recently, dbus compatible. And in fact, on Android, we speak to the dbus daemon we speak to BlueZ via the dbus daemon. So the Alljoyn daemon actually speaks dbus to the dbus daemon to talk to BlueZ for the Bluetooth functionality. So again, for those of you familiar with dbus, this object model should be familiar to you. The notion is applications expose their functionality via objects, and these are typically organized in some sort of hierarchy. And the objects implement interfaces, one or more. And these have 3 basic types of members. They have methods, signals, and properties. And so methods are your traditional remote method invocation, RPC mechanism. Signals are asynchronous notifications, so you register an intent to hear, or not an intent, that means something specific in this room. You register an interest in a particular signal and it will be delivered to you. And they can be broadcast, they can be multicast, which means they can be limited to a group, obviously, or they can actually be point-to-point. So a signal can be emitted to a specific party. And then properties are basically data members in a class in C++ or Java or something like that. And so you can kind of see the flow. So one application makes a method call, the bus routes it to the other application, the method reply goes back through the bus, the signal again goes through the bus and is delivered to some event handler on the receiving side. So security, I've touched on this a couple of times, right? What we're really looking for here is the ability for applications to interact at a peer level rather than having to pair entire devices. So authentication encryption, as I said, is intended to be app to app. The trust relationship is between the applications. It is not between the devices. And in fact, the bus itself is not engaged in any way. So the bus from this perspective is not trusted. It's only trusted to deliver the traffic. And then the other big point is device pairing is not required unless the transport requires it. So for example, on Wi-Fi, you still need to connect to the access point. We don't support ad hoc today. So you have to have that relationship with the access point. But on Bluetooth, for example, we typically don't need to pair. So you don't actually have to pair the devices to do Alljoyn exchanges over Bluetooth. The security is enabled at an interface level, so I talked about the interfaces in the previous slide, and authentication and key exchange is triggered on demand. So basically, if you try to interact with a secured interface from your application, that will trigger the authentication and the encryption. And so when you do have an interface like that, authentication is required to make method calls, and it's required to receive signals. And so when you receive a signal, for example, that'll trigger the authentication exchange with the peer. And once the authentication is done, all of the traffic is encrypted for that interface. So some performance and deployment considerations. So some things that we've done to make it work better in, for example, over Bluetooth, which is a fairly narrow pipe. We've implemented header compression, and the goal of this was to basically compress the messages down so they would fit in a single Bluetooth frame. There's a time to live message, so that allows support for isochronous data, i.e., media streaming, for example, or games where if the data gets there too late, it's pointless, so it'll time out those messages. And then we also added support for multi-point sessions. So that is what gives you this multicast. So all applications that are part of, for example, if you take a game as an example, the set of people that are participating in the game are the only ones that are going to get the signals, rather than everybody that may be on that bus. And the bus may be bigger because one of the participants in the game may have extended the bus to some other device, and they're interacting in some other way that has nothing to do with the game. So the multi-point sessions are really a way of creating a multicast group within the software bus. And the other big deal about that is that it allows you to detect when links are no longer being used, so you can actually shut the radio down. If an application is no longer interacting with any other applications out there, you can take down the radio link, which is intended to save battery power. And so these are all targeted at optimizing the experience on mobile devices that are constrained. So some deployment options. So there's basically 3 ways in the context of Android to deploy Alljoyn. One is platform integration. So the advantage of this is it gives you a single daemon on the system that basically supports all of your clients. And then it can use both Wi-Fi and Bluetooth in that case. And then in the future, it'll support Wi-Fi Direct as well. And the daemon would be started at system boot time via the standard boot scripts that launch everything else on the system. Another one is we have a downloadable APK. So you still get a single daemon in this case, but there is only Wi-Fi access. And the reason for that is in order to do some of the discovery stuff that we do, we leverage some functionality in Bluetooth that is not available via the Android framework. So you need to basically be able to speak to BlueZ directly to do this. And then the last one, and it gets launched by an intent. So an application can, and I mean an intent in the Android sense this time, an application can launch an intent, and that'll trigger the APK to get launched as a daemon.
I understand this logical setup that you're talking about, but what's happening at the Wi-Fi kind of physical side during this? So, for example, can I be associated with WPA access points and also have what's basically unencrypted transport to share with the other people out doing this that's not under WPA?
So we're not doing anything magic with the physical layer here, in Wi-Fi in particular. The magic that we're doing on Bluetooth is more about leveraging Bluetooth discovery protocols. Wi-Fi is an IP transport.
So the restriction is then that you cannot have your device hooked up to a WPA?
No, you can, any connection you have with an access point is fine. I didn't make this clear enough earlier. In terms of this pairing and whatnot, for Wi-Fi, you still need to be associated with the access point under whatever circumstances that access point requires.
Your peers on Alljoyn must then have the WPA.
That is true. You need to be on the same access point. And right now, the proximity piece, which I haven't talked a whole lot about, but today proximity on Wi-Fi means same access point. And there's various issues with that, which we can talk about later if you're interested. So the last one, so did I address your question? Okay. The last one is the bundle daemon. So we've actually, part of the issue that Alljoyn has is you have this dependency on this daemon. And so if you as an application developer want to create an Alljoyn app, and Alljoyn, we're still seeding the technology into the market, it's not guaranteed that Alljoyn's going to be running on, pick your favorite handset, right? So we put together this bundle daemon, which allows the application developer to actually bundle the daemon in with their app, so they're guaranteed that the daemon is there. And that is also launched by an intent, but it's only actually launched if the platform doesn't have one of the other two on there already. So you can still get the advantage, and the disadvantage is you get one, every app has its own daemon, right? And if you don't have a centralized daemon on the platform, they can't coordinate, and you lose the advantage of that coordination. But it will only get launched, the bundle daemon, if there isn't one central one already running on the platform. I.e., if you did the platform integration, you're good. When you send the intent, if the downloadable APK is on the platform, that will get launched. If none of that works, then the bundle daemon will get launched. So the way this looks from an Android integration perspective is that all the dark blue stuff is all Alljoyn related pieces, and all the light blue stuff is things that exist in the Android system today. And then the init scripts are sort of half and half because you need to modify the init script to launch Alljoyn. But so you have an Alljoyn enabled application at the top. We have an actual Java binding for that. And that sits on top of some Alljoyn JNI, which basically interacts with our C++ client library. So one of the things that Alljoyn gives you, and I didn't talk about this, is multiple language bindings. And today we support Java and C++. The native one is C++, which is what the client library is. The JNI is what JNI does. It translates between Java and C++. And then the client library interacts with the Alljoyn daemon. And then you can see, as I said earlier, if it's an integrated on the platform one, that interacts with the dbus daemon, which talks to Bluetooth, et cetera, et cetera. So this is what it looks like there. So availability. So Alljoyn is an open source project that's run out of Quick. We actually accept third-party contributions. So this is the homepage, www.alljoyn.org. So we do take third-party submissions from people. The source is actually available on GitHub. Why is this not? There we go. The source is actually available on GitHub. You can either download it directly, or we have it set up to use repo because we're actually using multiple repositories. And we actually have, and we also have binary SDKs, which are available on the alljoyn.org site that you can actually, if you don't want to build it yourself, we have binary SDKs for Android available. We recently released 2.3, actually 2.3.2 is a release we did a couple weeks ago. And the code is all licensed under Apache 2.0, so it's easy to use and easy to modify, and you can basically do anything you want with it. And that is it. So are there any other questions? If not, so I will be at the booth during lunch, you know, the 12:45 to whatever lunch. If you have any questions about Alljoyn or anything, feel free to stop by and ask me any questions that you have. And now I pass it over to Mike to be talking about. No problem.
Hello, everyone. Can you hear me? My name is Mike Mangan. I'm the FastCV product manager at Qualcomm, and we'll try and introduce you guys to our FastCV computer vision library that accelerates applications on mobile devices that are looking to basically enable computer vision type functionality. So what do I mean by computer vision use cases? A lot of folks in this room probably have different ideas, but what we're specifically interested in is computer vision use cases that are relevant to mobile users and can run on memory bandwidth constrained platforms like handsets. So in this case, many of you may be familiar with these. I'll just go through them quickly. Augmented reality is where you actually supplement essentially camera images with additional information to augment the information. We look at FastCV as being an underlying acceleration library that will allow that to occur, you know, even more efficiently in terms of both power and performance. Gestures, accelerating gesture recognition and the way people might use physical gestures of their device to essentially, tell an application something. That's another one. Face recognition, text recognition, pretty straightforward. Depth mapping for stereotype cameras is something we're looking at accelerating that functionality. And image stabilization is up there as an example of an image processing functionality that's within our FastCV library that we look to basically accelerate. So let me move along and try and get through this rather long deck in a relatively short amount of time. So again, we're focused on mobile. It's a library that is looking to hardware accelerate essentially some of these functions within our library. On Qualcomm hardware, we're going to use the, I'll get to it later, but we're going to use our application processor, our Neon SIMD engine, our DSP, and GPU over time. So these are essentially the hardware processing units that we're looking to accelerate some of our CV functionality with. So I'll spend a couple minutes on this slide just because I want to clearly articulate essentially the architecture. At the very top in this green horizontal row, we've got essentially the applications that we're looking to enable with FastCV. We could do this either directly. There's no direct link between the apps. If you had very sophisticated application developers, they might be able to take the functions that exist within our FastCV library directly and directly write applications, but it would require a degree of sophistication on the part of the developer that is rare. So we're looking at leveraging essentially middleware libraries, this second from the top orange row, and we have an example of that in the Qualcomm Augmented Reality SDK that's available for app developers to utilize. We actually today accelerate that using our FastCV library. And so underneath that, in the FastCV for Snapdragon and FastCV for ARM, what I want to make clear is we have two implementations of the same FastCV library. One is a reference implementation, FastCV for ARM. It will run on any ARM platform or ARM processor. It'll use basically just an ARM processor. There's no additional acceleration. What's interesting about that, and you'll see it at the very end of this slide, and we'll show real value to doing just FastCV for ARM, is the code is sufficiently well written for handset and mobile devices that you see a significant improvement over OpenCV, for example. FastCV for Snapdragon expands upon that for Qualcomm-specific chipsets. And like I was saying earlier, we use our additional hardware processing units on our SoC to help additionally augment the performance for FastCV for Snapdragon. And so at the bottom, you just have the various hardware units that we provide. Hexagon is a DSP, video cores, app processors, and the like. So the sound is fluctuating, so I apologize. But we have these various feature groupings for our library, and if you want more information on any of these, they're available on developer.qualcomm.com/fastcv. You can actually get very detailed information on every one of the functions. They're grouped in this particular way, and you can get the nth level of detail on each one of these. But I'll go through it relatively quickly here. So again, this is just expanding on the fact that FastCV for ARM just uses the apps processor, and Snapdragon takes advantage of both of all the different processors on our chipset. So where we fit in right now, many of you are aware of OpenCV. OpenCV is an incumbent library that has a very large set of functionality. We look at like the Kronos working group, and we're anxious to work with them to help create essentially a hardware acceleration layer that is essentially optimized, in our view, for mobile. It'd be great to have that capability such that you can actually implement some of these CV functions or use cases on mobile platforms. And we think that hardware acceleration is somewhat necessary for that. So we have our FastCV for ARM on the lower left orange box as a reference implementation. And then we're open to having a common API at the hardware acceleration API layer that various hardware-specific implementations could write to. And so that's kind of what we were thinking there. This is, again, just so, in case anybody didn't quite catch it, this is where we've got much more information if you don't certainly get to it in this presentation. So the next section of this presentation is to go in and have a look at some of the areas in these feature groupings that we were looking at and explain the actual library in a little bit more detail. So given that this is a technical audience, I'll go through it maybe more than I would to a marketing group, but I think that you'll still find it very high level. So It's C, C++ function calls. We try to make sure that the memory is 128-bit aligned. We end up having a very flat architecture in the actual library. It's thread safe, and we have separate functions for different argument types, so whether it's signed, unsigned, of various lengths. The API flow is extremely simple. You set a mode. You either select you're optimizing for performance, minimize power consumption, or offload from the CPU. Those are basically the three modes. Once you've set that, you can use any of the functions that are in the library, and then we handle cleanup with some memory, sort of memory care routines that we've got in here. So this is the set operation mode functionality, and you can see the type def there that basically explains how we have those three modes that I just articulated. And the memory management, it's FCV memalloc, so it basically allocates memory in a very aligned manner that's friendly to a lot of the functions that you're going to be using. You've also got a few macros in there and a pyramid allocation functionality so that you can actually set up memory for some of the pyramid type of data types that are valuable in computer vision. We have an FCV assert, and it actually doesn't completely exit. You actually just print a warning to the Android log, and this is useful for debugging your applications in a reasonable way, and you'd typically be able to remove it in production code. So there are, like I said, 8 different groups that we've organized the library into. Again, they're very much tailored to CV. They're primitive building block functions that are tailored to CV applications. And we won't go through all of them here today, but just to give you a flavor of what some of them look like, we'll go through the vector operations, the image processing, feature detect, and time allowing maybe 3D reconstruction, just to give you an idea of what's going on. So for vector operations, we have a number of different dot product functionalities where you take the dot product of two, in the first yellow circle, 36-byte vectors, and you can also do a dot product of 36-byte vector against 4 other vectors, 4 others. It's a way to basically make the most use in some cases of some of the 128-bit SIMD engine that we have in there, and so you'll see some of these numbers are carefully chosen for both computer vision uses and also taking into consideration the actual hardware constraints of a lot of mobile platforms. So in addition to just straight up dot products of vectors, we've got dot product of patches, and so this is particularly valuable. So you take a patch of an 8x8 square, and you can actually take that dot product along a line of pixels within an image, and that's pretty valuable for certain applications. But again, these are relatively low level. In image processing, we actually have a number of blurring or filtering functions that are of varying sizes. You've got median filtering and Gaussian filtering as well that are pretty useful. Edge filtering is also provided, so we've got Sobel and canny edge detection, and those are kind of like I guess you're getting the idea that if a developer was to basically use these functions directly, they'd need to be a CV expert, and hence what I want to make clear with this sort of going into the details of these functions, these are typically most valuable for middleware developers, like I was referring to on that stack diagram that we looked at earlier. You want to be able to create something like the QCar SDK middleware library that can utilize the FastCV functions and do so in an efficient way and essentially abstract that away from the end app developer that's more interested in user-level functionality. So image processing, we have many finite impulse response filters that are both, they provide correlation with separable and non-separable kernels of different sort of sizes. So you can do 3x3 all the way up to 17x17 correlation calculations. These things are getting done repetitively in a lot of CV apps, and so making these base primitive functions extremely efficient is one of the real value adds that FastCV brings to bear. So it's actually quite an efficient library that we'll demonstrate with the performance deck at the end, or a slide at the end. We'll show you that. In image processing, for Viola-Jones algorithms that you might be familiar with, a lot of these summed area table functions are particularly relevant. And again, these are over a variety of sizes. And we actually do handle the unique case where in memory you've got contiguous memory. You can actually essentially do an integration over a straight line in memory and actually get some significant performance benefits in that particular function. So it's the second yellow from the bottom, that FCV integrate image line, that's the one I was referring to, and it's actually a particularly valuable one in some of the applications like gesture recognition. So what's valuable in a lot of augmented reality use cases is feature detection and tracking, and so you know, feature detection at a very base level is provided in our FastCV library. We do not aggregate this. That's left up to those middleware libraries to be able to provide that kind of feature detect and tracking functionality that an augmented reality app would need. But again, our Qualcomm augmented reality library or middleware library takes advantage of FastCV to implement its feature detect and tracking algorithms very effectively. So this Fast9 detect is one example of that, and we've got, you basically can do it in Fast9 corners from the image. You can do it in a masked way, so essentially you set regions within the image and you basically mark it with a 1, and then you only do Fast9 corner detect on that region. That's sort of called masking, and then you can do essentially Fast9 corner detect and scoring simultaneously in some of these later functions. So I'll skip the 3D reconstruction one just because some of these things are, you know, you have to be specific to the CV domain to be particularly interested. But what I wanted to make clear is we do have some very basic data structures that are used repeatedly through a number of these functions. FCV correspondences are used in some of those, actually, I'll go back to it. 3D reconstruction, and so you can see there that we're using this data structure FCV correspondences quite a bit, and in these sort of geometry affine, you're doing affine transformations, and you basically do that on a given correspondence feature set. So, and then the pyramid level ones, one I referenced earlier. So we do have FastCV available for download on our developer.qualcomm website right now. You can actually install a sample application. I think this is fairly basic stuff for people that are familiar with development on mobile handsets, given that this is the Android Builder Summit. This is clearly not the best use of your time, but I wanted to make clear that we do have some detailed examples of how to basically link in our FastCV library into our sample application, which does fast corner detection and uses some of the functions within our library just as a way to get people started. And so feel free to download it and give it a try, and try it on your actual phone. It's very easy to do. So just to go through some of the sample application code, if you were to look at the source code which we provide in that downloadable SDK, there is lots of code, but there's only very little FCV code, which shows you that a little goes a long way in this particular example. You've got set the operation mode, which is actually in here, like I was describing earlier. You've got, essentially, you align FastCV align 128, you do that. And then essentially, at the bottom here, we're doing a color conversion from YUV to RGB, and then we do filter the image a little bit, and essentially then we do corner detection. And so it's very, very small amounts of FastCV code that you can include into an existing app and get some significant speed up in terms of performance. And we've got commercial examples of people that have actually taken existing apps, refactored them to include FastCV function calls where they had bottlenecks, and we've observed, you know, north of 30% improvement in an individual app just by basically, you know, removing essentially a bottleneck in their app and putting in another one. So, as Jenny Craig would say, results not typical, but actually we think we can do a lot better than just 30% with some more significant refactoring. So I'll move along to how how, this is probably an issue that's top of everybody's mind. If you have an actual existing CV application that you've developed or prototyped using OpenCV, it's not black or white, you use FastCV or OpenCV. You can actually profile your application that you've prototyped it maybe on a machine and seen some performance bottlenecks in, for example, color conversion or pick your area. And what you can do is actually essentially replace that particular function call, link in our, with a FastCV function call, and you can do that by linking in essentially FastCV library to your application, calling the appropriate function, seeing for yourself if you actually get a demonstrable or a relevant improvement. And we think that you will see such. It's actually been a couple of good commercial examples that we've got that have done this, and they've combined both OpenCV, FastCV, and some proprietary algorithms that they've, collected together to create their application and seen some good results by using FastCV. And so, as I promised, we wanted to basically make clear that there's value to both the FastCV for ARM as well as the FastCV for Snapdragon. And so we normalize some of these performance results with OpenCV, and I should be candid and say that these results are significantly out of date. Like, they're a couple months old, and we've significantly improved our performance since then. But even 2 months ago, we actually, you get the point. OpenCV, if you normalize all of these results to 1, you see that FastCV is generally a significant improvement over OpenCV on a mobile platform. And then if you actually use some of the actual hardware acceleration that's provided by FastCV for Snapdragon, you end up getting even better performance. So I think it makes a compelling case for using FastCV. And so I wanted to make clear an additional point that is very, very valuable in the mobile-specific CV application development domain, and that's power. And so there are multiple ways in which you can actually sort of get a benefit from FastCV. One of them is in raw performance improvement, which was demonstrated on that previous table. But the second, and what we're using here, is essentially this green graph, CPU frequency, as a proxy for power consumption on the mobile device. And so if you have an algorithm that's basically running for a long period of time, you can actually clock the mobile processor very high, get it over with very fast, and then you actually reap the performance benefits of FastCV in that dimension. And then you finish your algorithm quicker, and then you can shut it down. And so as you see this green line coming down, you basically realize the application finished that blue task, and essentially you can downclock your CPU, saving power as a result. And that basically is it. There's additional benefit to shorter algorithms, and you can see that the dynamic clock scaling essentially reaps you a significant power benefit by having something like FastCV in there. And so that was the main point of this particular slide. And so I wanted to basically stop there and say thank you guys for listening, and by all means, if you have any questions for either me or Marcello, by all means. Go ahead.
So I think for 3D construction, you have the feature detection, but I didn't see anything on the feature matching. And one of the issues, like with OpenCV, is there's a whole bunch of different feature matching algorithms, surf and SIF.
Yeah.
But some of them are patented, even though the code is open source. So are there any licensing issues with this in terms of that kind of stuff?
FastCV for Snapdragon is licensed free of charge, but it's basically a Qualcomm proprietary license. So if you were to integrate this into your actual application, there is no royalty or fee or anything of that sort that you would have to pay.
Be concerned about somebody else's
You would have to be concerned about it. We basically disclosed all of the actual patents that we have referenced in our implementation, and so to the extent that you have additional ones, you would basically have to be aware of those. But we disclose completely everything we've kind of referenced. And like you said, there are some interesting issues in the sort of patent space in this area. But a lot of the stuff that we've pulled in, we've completely rewritten for the mobile area. And so, like an example would be Lewis Canade or KLT or something like that, where you end up having like the professor essentially released the source code, but we've taken his code, we've acknowledged that we've looked at his code, and essentially we have rewritten it completely to be optimized for mobile processors. And yeah, go ahead.
For your last slide, you mentioned switching to the performance governor for certain tasks that are very CPU intensive. Now, some of the other CPU scaling governors, like on-demand, will dynamically scale the CPU based on load.
Do you see a large difference in performance when using an on-demand governor as opposed to just switching to performance for these kind of scenarios?
I must be honest, I'm not entirely familiar with exactly the performance issues of an on-demand governor. What I am familiar with is essentially the dynamic voltage and clock scaling that goes on with essentially our apps processor. And so to the extent that we see significant benefit to finishing certain tasks very quickly. And so I really can't really answer your question. I couldn't draw a comparison. But go ahead.
Yeah, just want to look. Do you have a roadmap to implement this as Java classes?
Performance is our main consideration. So a short answer is basically there is none right now, no. We're looking at keeping it as a C, maybe some C. We're trying to basically keep it very platform portable and optimizing for performance on mobile devices. So I think the answer is we're basically going to try and keep it that way.
I only ask because it's an Android summit, so.
No, we Jay and I. Anyways, sorry. Any other questions? That's it. Thank you very much.